What specific problem does the proposed method in this paper aim to solve regarding the phenomenon of grokking in neural networks?
The proposed method in this paper aims to solve the problem of delayed generalization in neural networks, specifically addressing the phenomenon of grokking, which is often hindered by softmax collapse (SC) and naive loss minimization (NLM). SC occurs due to floating point errors that lead to zero gradients for the correct class, effectively stopping learning and preventing grokking. The paper introduces a new optimizer, referred to as one-number-one-grad, which updates weights based only on the orthogonal component of the gradient, thereby avoiding the NLM direction that causes SC. By mitigating these numerical instabilities and the effects of NLM, the method enables models to achieve generalization without the initial overfitting phase typically associated with grokking. This approach demonstrates that grokking can occur even in the absence of regularization, challenging previous assumptions about the necessity of weight decay for achieving generalization.
How does the proposed method work? Illustrate the algorithmic steps taken by the authors to address the identified issues with softmax collapse and naive loss minimization.
The authors propose a new optimizer, referred to as one-number-one-grad, which specifically addresses the issues of softmax collapse (SC) and naive loss minimization (NLM). The algorithm operates by updating the weights based solely on the orthogonal component of the gradient, effectively projecting the gradient onto a hyperplane that is orthogonal to the current weight direction. This projection prevents the model from scaling the logits in a way that leads to SC, which occurs when the correct class logit becomes significantly larger than others, resulting in zero gradients and halting learning. Additionally, the authors validate their approach by demonstrating that using one-number-one-grad allows models to achieve generalization without the initial overfitting phase typically seen in standard training methods. The results indicate that this optimizer facilitates grokking in scenarios where it would not normally occur without regularization, thus providing a robust solution to the identified problems.
Can you provide a concrete example illustrating the inner workings of softmax collapse and how the proposed solutions mitigate its effects?
Softmax collapse (SC) occurs when the logit for the correct class in a neural network becomes significantly larger than the logits for all other classes, leading to zero gradients for the correct class and halting learning. For instance, in a scenario where a model achieves 100% training accuracy, the gradients may align with a direction that scales the logits, resulting in SC and preventing grokking. To mitigate SC, we propose a numerically stable version of the softmax function, termed STCE, which reduces the risk of absorption errors by transforming logits into probabilities in a less extreme manner. Additionally, we introduce a new optimizer, one-number-one-grad, which updates weights based only on the orthogonal component of the gradient, effectively avoiding the naive loss minimization (NLM) direction that leads to SC. These interventions allow models to generalize without the initial overfitting phase typically associated with grokking, demonstrating that SC can be circumvented even in the absence of regularization.
What practical benefits does the new optimizer, one-number-one-grad, offer compared to traditional optimizers in the context of grokking and generalization performance?
The new optimizer, one-number-one-grad, offers significant practical benefits in the context of grokking and generalization performance by specifically addressing the issues of naive loss minimization, NLM, that traditional optimizers often encounter. Unlike standard optimizers, one-number-one-grad updates weights based solely on the orthogonal component of the gradient, effectively preventing the scaling of logits that leads to softmax collapse (SC) and subsequent overfitting. This targeted approach allows models to achieve generalization without the initial overfitting phase, typically seen with traditional methods. Experimental results indicate that models using one-number-one-grad reach 100% test accuracy more rapidly and consistently than those employing standard optimizers with weight decay, which often require a longer trajectory to minimize both training and test loss. Overall, 1 grad facilitates a more direct path to generalization in Grokking tasks, demonstrating its effectiveness in overcoming the limitations of conventional optimization strategies.
How did the authors validate their findings regarding Softmax Collapse and the effectiveness of their proposed modifications? What experimental setups were used?
The authors validated their findings regarding Softmax Collapse, SC, by conducting experiments that demonstrated the relationship between floating point errors and the absence of Grokking. They trained a multi-layer perceptron, MLP, on modular addition tasks without regularization while varying floating point precision, observing that SC occurred when the dataset size decreased, which inhibited generalization. To further validate their hypothesis, they introduced a numerically stable version of the softmax function, denoted as 2, and showed that replacing the standard softmax with this new formulation led to Grokking in scenarios where it was previously absent without regularization. Additionally, they developed a new optimizer, 1 grad, which preserves only the part of the gradient orthogonal to the direction of naive loss minimization, NLM, demonstrating that this approach allowed models to generalize without the initial overfitting phase typically associated with Grokking. The experimental setups included training on commonly studied Grokking datasets, using both MLPs and transformers, and comparing the performance of their proposed methods against traditional approaches like AtomW and SGD with weight decay.
What are some limitations or potential gaps in the proposed approach, especially regarding its applicability across different datasets or model architectures?
The proposed approach primarily addresses the phenomenon of Grokking through the introduction of a new optimizer, 1 grad, which mitigates naive loss minimization, NLM, and Softmax Collapse, SC. However, one limitation is that the effectiveness of this optimizer may vary across different datasets, particularly those with varying complexities or sizes, as the paper indicates that Grokking is more prevalent in smaller datasets. Additionally, while the findings are validated on specific models like multi-layer perceptrons, MLPs, and transformers, the generalizability of the approach to other architectures, especially those with non-homogeneous structures or complex skip connections, remains uncertain. The paper also suggests that while weight decay is often necessary to induce Grokking, it is not universally applicable, indicating a potential gap in understanding how different regularization techniques might influence Grokking across diverse scenarios. Lastly, the reliance on floating point precision and numerical stability raises concerns about the robustness of the approach in practical applications, where hardware and implementation differences could affect performance.